James Webb is making its way towards its final orbit around Lagrange 2. And of course, we've all been following the unfolding space origami that they have been doing out in space, getting that telescope out into its operating condition. But there's actually been a lot of other stuff going on during the unfolding process, and there's a lot of stuff still to do before they can do any kind of science pictures. Today I'm going to show you what the first pictures from James Webb is going to look like, and I'm also going to explain to you why they will never be released to the public. And we're also going to take a look at what the whole mission in James Webb is actually about. So while James Webb has slowly unfolded itself doing its journey out to Lagrange 2, an interesting thing that they've been doing is they have been cooling down the telescope, as you would expect. I mean, James Webb is an infrared telescope, means it's looking at basically heat radiation coming out from the universe. And you can imagine you're going to need a very, very cold sensor in order to be able to take pictures of very, very cold objects. So they're actually going to cool it down, I think it's to around 50 Kelvin or 50 degrees Celsius above absolute minimum. So it's going to be a very cold telescope. But during the cooling process, they've actually been heating up the telescope. The reason they've done that is they were afraid the telescope would cool down too quickly. After it was built on Earth, there could still be pockets of air trapped inside the telescope. And if that was the case, and they cooled it down too quickly, that air would condensate, and you would get water or ice build up inside the telescope, which would obviously be very, very bad. So therefore, they've actually had heaters on inside the telescope to keep it hot and to then slowly cool it down over like a month to make sure that all those air pockets that may still be inside have time to evaporate out into space. But once they reach L2, one of the first things they're going to do is they're going to, of course, need to do a number of tests to make sure that everything is working as they are expecting. First thing they're going to do is they're going to make sure that the telescope can actually log on to a target and track it. So they're going to find a nice bright star, they're going to ask James Webb, log on to that, and then they're going to take a picture. And that picture is going to be a horrible mess. I'm going to actually show you a simulation I made of it. It's going to look something along these lines here. What we have here is 18 copies slightly moved off from each other of the same picture, then stacked on top of each other. Now it looks like this because the main mirror, of course, consists of 18 smaller mirrors, and during the launch process they could have been slightly moved, or especially the mirrors out on the side that has been folded out. I mean, that's a mechanical process, and there's gonna be some give in it, and if they're not spot on, well, the picture is not gonna look great. So they have thought about this, and they are planning to calibrate these mirrors once it reaches its orbit. So the picture we see here is actually because all these mirrors are slightly out of alignment with each other. So what they're going to do is they're going to take and move one of the mirrors, and then they're going to take another picture like this, and then they're going to see which dot moved, and then they're going to figure out, okay, so that dot belongs to that mirror, so we can now move that mirror into the center. Then they're going to do the same thing, and they're going to repeat that process 18 times over and over and over again until they have slowly moved all those mirrors in position so that they're all aligning up with each other, and they have all the mirrors pointing at the exact same spot on the center. This process, along with a number of other tests, is going to take around 3 months after it reaches L2, which is about 1 month into the mission. So at this point we're into month number 4 after launch, and they're done with their alignment of mirrors and the basic tests. The next thing they need to do is they need to go and spend time calibrating the mirrors. You know, if you do astrophotography, that we do dark frames, we do all flat fields, we do all these things. They're of course going to have to do the same thing with James Webb, and as always, as we've all been told, you have to do your darks and your flats and your bias frames in the same environment. And the way I understand it is they're basically going to take the camera, all the different cameras and scientific equipment, all the different mode of operation. They're going to do all these calibration frames at the start, and then because it's going to stay in that same environment, they can reuse them, and they don't have to take biases and flats and those kind of things over and over again after each mission. So that's what they're going to be spending, I think, another month on at this point. So it's going to be like, that's month 5, so it's going to be into like month 6 after launch before we begin to see any real science coming out of James Webb. But what is James Webb going to look at? Well, James Webb, as I said, is basically a big thermal imaging telescope. It looks at heat signatures from some of the earliest galaxies. Now, the reason why it looks in the infrared And of course, because first of all, we didn't really have any good telescopes in that area in space. I mean, we have Hubble that kind of covers the visual. We have WMAP up in the microwave area that be looking at the cosmic microwave background. But we kind of missed something there in the infrared area, and that's the gap that James Webb is going to be covering. And what it's going to be looking at is the light from these early galaxies in the beginning of the universe. This will of course been traveling for billions and billions of years, and over the time the light will have been redshifted, so it will be moved down to these longer wavelengths. That's why we're looking in the infrared. Not because the galaxies originally emitted infrared light, but it has been redshifted into the infrared area. Hopefully it's going to help us understand the evolution of galaxies. We know surprisingly little about how galaxies evolve, and understandably so. Imagine you had to try and understand, you came as an alien to Earth and you need to understand the evolution of a human being. How does a human age? But time stood still and you could only see a snapshot of the Earth. And now you have to go around, look at humans at different ages and figure out which one are the younger one, which one is the older one, how do people age? That is the problem that we have with galaxies, that they evolve so slowly that even over our lifespan of the human race, there's basically been no evolution in galaxies because it's a blip in time for a galaxy. So therefore, we need to look at galaxies in different stages. So looking at these early galaxies in the very start of the universe, we know that must be young galaxies. And that's going to give us a reference point saying, so this is what a young galaxy looked like, and that hopefully is going to help us understand how galaxies evolve over time. And I'm pretty sure that some of the first pictures we are going to see from James Webb is going to be pictures of some of these early galaxies. I think that will be some of the first pictures they're going to release to the public. I don't think we're going to see these calibration images being released. I think that's unlikely. This is a science mission after all, and they want to get their name on any discoveries made with James Webb, so they're only going to release like press images and stuff like that. And I don't think the press is that interested in calibration pictures. But I'm very much looking forward to seeing what James Webb comes up with over the next, hopefully, many years. Same thing happens here when the plasma from the sun hits the Earth's magnetic field. It has a hard time going across the field lines, getting down to the surface. So you can imagine that you could kick the ball so hard that it would leave the Earth's atmosphere, never to return.